in this video, I want to find both the relative min and max of the function and the inflection points of the function. And so that way we can kind of compare the two and see how all three, the function, the first derivative, the second derivative, how they're all connected, how they're all related. Okay? And we're going to use the first derivative test to find the relative min and max in this case. And in the next video, I'm going to introduce the idea of the second derivative test, and we're going to see that that's actually a little bit easier to use. But the problem with the second derivative test is it's not always conclusive, and in those cases you have to use the first derivative test in order to determine a relative min or max. So, okay, so we got a fourth degree polynomial. So I'm going to first take the derivative, and what I'm going to do is I'm going to find the relative min and max, and then I'll find the inflection point. So take the derivative, and I get that. So now I need to solve the derivative for 0. So set equal to 0. So that's a cubic, but fortunately I can factor out one of those x's. And then I'm just left with x squared minus 1. Okay, so then we got 4x, x plus 1, and x minus 1. Okay, so then the derivative then will be equal to 0 when x is equal to 0, x is equal to negative 1, x is equal to positive 1. And so these are the critical points of the function. So now let me set up a table to determine if they are relative min or maxes. And I'm seeing here that the video is not as clear, it doesn't seem. So let me actually, I'm going to let it, see if it can do, okay. There, that's pretty good. That's better. Okay, so now I'm going to set up the table then. So it'll be negative infinity to negative 1, that open interval. And this is for the critical point x equals negative 1. And then negative 1 to 0. Okay, and that's for the critical point 0. 0, positive 1. And that's for the critical point 1, and 1 to infinity. Okay, and so let's just, I don't know, we can pick x equals negative 2 as my test point there, and this would have to be, I guess, x equals negative 1/2. This would be x is equal to 1/2, and then x is equal to 2, and then you'd plug these in. Another thing that I can do with this cubic, let me show you. Another thing that you can do is I could say these are the zeros. So here is negative 1, there is 0, and then there is positive 1. And so these are zeros. So you can do this when your function is a polynomial, because like a cubic polynomial with a positive leading coefficient would have to come down here, and if it has to pass through the axis in each of these places, it would have to go like that. And I'm not saying this is exactly how high or how low they go relative to one another, but the point that I'm making is that these are like these 4 places in the these 4 intervals here. And so I can see that it's negative here, positive here, negative here, positive there. So this is just a speedy way. Okay, so that's the function. It's going to look something like this, at least when it's below and above the axis. This is when this cubic will be below or above the axis. And so this is a quick way, instead of plugging each one of those into there, it's a quick way of determining it. And you might be thinking, well, it's easy enough to just plug them in there and find out the sign. And that's true, you can do that. But as far as me doing this problem, I wouldn't even draw this out. I would just see this in my mind and see the polynomial like that, and I would know that it was negative, positive, negative, positive. Okay, so what this means, it goes from a negative to a positive, so this is a min. Positive to negative, this would make it a max, and then this would be a min. So it's going to have a relative min, a relative max, a relative min. Okay, so those are the relative min and maxes now of the function. Now let's find the inflection point. So an inflection point is when the derivative, when the derivative, if it has a relative min or a max. Okay, and so it's going to be the critical points of this derivative, or it's when the second derivative is equal to 0. Now, when the second derivative is equal to 0, that could be a critical point, but it doesn't mean that it's a critical point. So let's actually find the second derivative. And when I do this, I get 12 x squared minus 4. Okay, and then what I'm going to find here is, okay, I'm going to set this equal to 0. So 12x squared minus 4 equals 0. And I can pull out a 4 here. And then I'm left with 3x squared minus 1 is equal to 0. And then what we see here is, I suppose I can factor this. 3 square root of 3x plus 1 square root of 3 times x minus 1 is equal to 0. So this is actually going to give me a critical point of the first derivative. It's where the second derivative is equal to 0. And this one would be like negative 1 over the square root of 3. And I could rationalize the denominator. I'm not going to worry about that this time. This would be 1 over the square root of 3. So these are actually the critical points of the first derivative. And so in order to determine whether or not those points are inflection points, I got to see if the first derivative changes signs. Or in other words, I got to see if these critical points actually result in relative min and relative max of the first derivative. So I'm going to make myself a little table. This would be negative infinity to negative 1 over the square root of 3. And then I would have negative 1 over the square root of 3 to positive 1 over the square root of 3. And then I would have 1 over the square root of 3 to infinity. Look like that. Okay, and now this thing is a parabola, and these two are the roots. So you would have like a root here and a root here. So I'm going to use my little method that I was showing you over here. So this is like a parabola, and it's open upward, so it really goes down like this. So what we see is that it's positive here, negative here, and positive there. And so what I can see here is that both of these are inflection points, right? Because it's changing sign. In this case, it's going from a max to a, it's going from the first derivative is going from increasing to decreasing, so that's the first derivative. Here it's going from decreasing to increasing. So in each case, both of those are in inflection points. So inflection points would be x equals, and you could plug those into the original function. So let me actually do that. Negative 1 over the square root of 3, and I'm going to plug them into here. And notice that both the negative and positives are going to give me the same value. So I'm going to do negative 1 over the square root of 3 to the 4th minus 2 times negative 1 over the square root of 3. Oop. That squared. So in other words, I just put the thing into the, I'm putting it into the original function because I want to find the point on the graph. And it looks like this is like negative 5.89 if I round to 2 decimal places. And then the other one's going to be the same, because when you take it to the 4th and square, you'll get the same thing as if you put in a negative as you do a positive. Okay, so these are the inflection points on the original graph. So now let's graph. So these are the relative min and max, negative 1, 0, 1, and then these are inflection points. Let me actually find out where that occurs. So if I take 1 divided by the square root of 3, it's like 0.57. So the inflection points are actually in between these critical points. It's between 0 and negative 1, 0 and 1. So let's graph our function. So I got x to the 4th minus 2x squared, and then I'm going to do like maybe a regular window. And here we see that we have min at 1, so if I hit second calc, so if I hit negative 1, that's a min. If I hit a positive 1, that's a max. At 0, I'm sorry, both the negative 1 and positive 1 are min. The 0 is a max. That's what's being shown here. Now those inflection points, what I'd like to do is zoom in on the graph, because they're in between 0 and negative 1 and 0 and 1. So maybe I'll go between negative 2 and 2, and then we'll do this between, I don't know, negative 3 and 3, something like that. And so we do see that this thing is concave up, and then somewhere there it has to change its concavity so that it's concave down, and then it has to change its concavity over here so that it's concave up again. And those points we've determined are 1 over the square, negative 1 over the square root of 3 and 1 over the square root of 3. So negative 1 divided by the square root of 3. And so hit this, and I see that I get, oh, I got negative 5 repeating. I didn't get this negative 5.89. So, but that does look like the inflection point. So I got the inflection point wrong. It's just down here. I must not have put it in my calculator right. Okay, and then if I do positive 1 over the square root of 3. There's the other one. Okay, so now let me see why that didn't. Well, I evaluated the graph at that thing, so I'm not sure. Let's see if I quit this. Do I see what I did here? Negative 1 over the square root of 3 to the 4th minus 2. Oh, I got, this is 1 times the square root of 3. That's the problem. So I put that in wrong. Oop. So let me go over here and then second insert, put a divided sign, and there I get the negative 0.5 repeating. So this should be negative 0.56 if I round to 2 decimal places. Okay, that's actually like 1/9 or 5/9 or whatever is where that is. So there you go. And so you see how all these, the technology, the math, calculus, all of this is working together, right? And you catch your mistakes, one thing catches the other, and they're all going hand in hand. That's the beauty of this. And also to find these points, the exact values for where it changes its concavity, very cool. It's the calculus that allows us to do that. So, so very good. So we're going to look at the second derivative test. I was going to do another example here where it did not have any relative min or maxes, but it did have an inflection point. But I think this is good. I think we should move on now and look at the second derivative test.